can see it on YouTube. I'm going to press go live, and we are now live on YouTube. So, hi everyone, this is the 45th edition of our Starknet Community Call, and today I'm joined by David and Elon from StarkWare. Hey guys.
Hi, how are you?
So, today's topic is going to be, I really like, when we do community calls, we often get different kind of stuff. We get people presenting their projects, we get people building on Starknet, and then from time to time we also get people from StarkWare presenting in depth what they're building for Starknet, or like the backend, the stuff that you actually use every day but you don't really understand. And today is going to be one of those calls. Today we're talking about dynamic layouts, which is a bit of a foreign topic, I guess, for most people. So we're going to explore this. To the people in the audience, feel free to ask questions. You can ask them on Twitter. You can ask them on YouTube. We'll be monitoring them, and we'll answer them once they come. Before we start talking about dynamic layouts, I'd like to hear a bit more about you, David and Ellen. So, David, can you start? What do you do at StarkWare, and how long have you been there?
Thank you, Eli. I'm David. I work in StarkWare since 2018.
Mm-hmm.
I am the team lead of the Builtins team, which for a while is working on the dynamic clouds. That's me, Alon.
Okay, very nice. Alon?
Hi, so I'm Alon. I've been in StarkWare for, I think, about 3.5 years. I work under David on the Builtins team. I've also worked on several other projects within StarkWare in the past.
Oh, so you both have been here for a very long time, and I guess you must have seen quite a lot in the evolution of, the overall proving system that we have in place at StarkWare, right? Because, I mean, to the best of my knowledge, it's one of the only proof production system that is live. I don't think there are many instances of people proving stuff, and so you've seen it rise from nothing basically to where it is today. I'm curious. Can we? So, David, you mentioned you guys are working. You're in the Builtins team. Is that correct?
This is correct. Yes.
Nice. So, can you explain, please, in a few words, what are Builtins for people who are listening, who are new to Starknet?
Of course. Well, first of all, I assume that the audience has met Cairo, which is a great programming language which is used to define statements that we want to prove. Now, from these statements to actual proof, we have all this proving system, which is based on a protocol called Stark. And you can think of the Stark as proving a virtual machine. We call it CPU-R, this virtual machine. And this machine is static. It has very specific. It's like a chip that has a very specific circuit. But the programs are they are dynamic. You have these programs that are written by the developers. They change in every proof, so we can think of them as loaded to the memory of this virtual machine, and the Stark protocol is proving the execution of the virtual machine on a given program. Now, these programs.
So it's kind of like if I have a laptop with a CPU, I can run Windows or Ubuntu on top of it. It's the same CPU. It's just what matters is what I load in the memory when I start executing it.
Exactly. And this CPU has native opcodes, right? It has addition, it has multiplication, it has memory access, but sometimes there are functions that, well, how you say it, sometimes you want to implement complex functions, right? What happens when you implement complex functions on CPUs? It will always be less efficient than implementing them in hardware, right? So,
Instinctively, I would have thought that this is for dumb operations rather than difficult one. Like if we make the parallel with the Silicon world, one example many people in the blockchain world are familiar with is SHA-256 hashing. You used to be able to mine Bitcoin, for example, with your CPU, and now it's very much. I mean, you can still do it, but it's not efficient because it's much, much faster to do it with ASICs, application-specific circuits. But this is for relatively dumb operations, right? You're doing always
well,
the same thing, but I mean,
this is a great example. This Chateau is exactly what I call complex, because it's not
okay.
a simple rotation or a simple addition or a simple XOR. It is something with that is more complex to define, to express. Okay, so this is a great example. It is exactly what built-ins are for. So in an ASIC is exactly the hardware hardware solution for SHA-2. You can also have CPUs that have SHA-2 specific opcodes that are called intrinsics in the Intel design. So these intrinsics in the Stark world, we call them builtins. It is operations that are not native to the machine, but we do implement them in the machine, in the lower level, in the hardware. It's not really hardware, but it's the analog, and this way we allow the program to use these specific intrinsics or built-ins with the efficiency of the lower level, but with more logic that can be added in the programming language.
Nice. Okay, so for some repetitive operation that are resource heavy for a CPU, you get this kind of shortcut where you execute it for much cheaper. Okay,
Exactly.
so these are what built-ins are. Yeah, I tend to think of them as like external component to your CPU, but intrinsics.
So I think a good analogy that we like to use is memory mapped devices. If somebody might remember how you used to communicate with monitors in the past, you would just write to a specific region in memory, and the monitor will display those bits on the device itself. So a built-in operates in the technical sense, and just a little bit under the hood, a little bit like this. We write to a specific region in memory where these specific constraints for the implementation of the Starks apply, and then we're able to perform these operations kind of externally to the CPU. We communicate with it via memory.
Interesting. Cool. So, okay, I think we've introduced nicely what are built-ins. Now, can you explain a little bit how do you use these built-ins right now in the proof system, and what is the layout?
Okay, these are two different questions.
Oh.
For the first question, for example, we have this the bitwise built-in. It's a built-in that takes two field elements. and returns the end and the bitwise end of these two elements, the bitwise XOR and the bitwise OR. These three operations are very non-native for algebraic circuits because they are very far from being related to polynomials over the field. This is why it is a bit inefficient to implement them, and that's why we need this speed up of doing it using a built-in. On the other hand, they are very basic in programming languages and basic computations. For example, we can use them for Chateau. For example, we can use them for Ketchup, for Blake, or any other modern hash function. Well, not every, but many. So using this shortcut, we actually developed many such hash functions, which are widely used in cryptography and many things that you want to prove actually.
Understood.
And for the second question, I'll repeat the question because it was a long time ago. What are actually dynamic layouts?
Right? Or layouts in general.
Layouts in general. So this virtual machine, it has specific configurations, we can say, some parameters, just the same as CPUs are different. So also this machine can have several static layouts which define the exact way that the CPU is defined. For example, one parameter that is defined there is the ratio of every built-in. How much of the built-in is being used in the machine relative to the number of steps. So in the static world where we define this layout statically ahead of time, we need to predict how much of each built-in will be used in the future programs.
But I don't understand why you have to fix this. Why do you have to define in advance how many you'll need?
Okay. Just like you have a specific number of registers in your CPU, and you have a specific number of ALU components in your CPU, and you can have up to as many threads in parallel in your CPU. All of these things are static. They are part of the
threads.
CPU.
The threads I can use one or two, or I can instantiate one and reuse one.
But they won't be really in parallel. If you only have, for example, 8 cores, then you can have more than 8 actual processes in the same time. You will have them waiting for each other, right?
Okay.
So such parameters are actually static in the definition of the machine.
Understood. Okay.
So if you write a program that uses more than 8 threads and you run it on a machine with 8 cores, it will work, but it will be less efficient than a machine that is dedicated for this program, right?
Yeah.
The same way we have the layouts can match your program, but it can be, if it's not an optimal configuration, then it will still run, but it might be less efficient.
Okay, understood. I think the example that was given, we had the blog post a while back, and not so long ago, but a couple of weeks ago, and one of the example that was given is that there's X amount of that much of a specific built-in, and if you use less of it, it still takes some space, but so it's less efficient, I guess. I don't know.
Yes, a very analogous example is, for example, with this Chateau ASIC that you mentioned. Assume that you have a program that is using many Chateaus, right? So you will use a CPU that has some of its silicon dedicated for Chateaus. But if the ratio of the Chateau executions relative to the with respect to the other opcodes that are run, it's not if it's not if it doesn't match the CPU, then what you'll have is that maybe lots of time this Chateau component will be unused, for example, and then it will be less efficient. For the same reason, it will be in the virtual machine.
I think for us there is an even, it's kind of worse than just having an unused SHA-2 component, because in a normal CPU, when you think about an unused SHA-2 component, it just sits there and does nothing for part of the time. But we have to represent the entire trace. So for us, we have to copy the whole machine for every step of the trace, or for every number of steps of the trace. So if we have a ratio of SHA-2 components, if you will, if we have a SHA-2 designated for each 16 steps, or for each, it's going to be a SHA-2, it's going to be something that's more error friendly, but for each 16 or 256 steps, then we have to copy all of these every time. So this waste accumulates the more steps you make without using the component. It's not just
Makes
once.
sense. Yep, I remember.
I will say even more. If you don't use this Chateau component in the CPU, then you could have used the silicon for another core, for example, right? For another thread, but you don't, because you have it dedicated for Chateau.
I remember a while back I was asking somebody at StarkWare, okay, but built-ins, eventually we're going to have thousands of these, right? And he told me, well, not really, because for each built-in you add, it takes some space. And if you don't use it, I mean, it's nice to have, but if you don't use it, it wastes space. So it's not feasible, right?
Right, exactly.
But then eventually he told me, actually things might change, which I guess is what dynamic layouts enable, or not really. How did you come up with the idea of dynamic layouts, and what are these? Two different questions again.
I think it's these are related questions. Unlike the hardware world, where you in order to build the chip after you write the program for it, then you have to physically build it. In our world, it's all programs, so we can actually, and we do. It's not in production yet, but it is going to be. Define the layout after we measure the execution resources of the program.
It's true. It's so weird when you think about it. But that's something I really find fascinating about proving, is that it turns a lot of assumptions you may have on your head. Like I don't know. I feel like the way you approach proving a problem is sometimes very different than how you approach running a program. You want to prove that you run it, but you approach it differently. Okay, so it's kind of the same with with proving for
for example, if you
specifically.
want to take a square root, then you only need to provide the answer and prove that squaring
Exactly.
it
Yeah,
is
hints are the same. It's kind
is
of
the
like,
input.
I already have the answer. I just need you to prove that it's the correct one, no matter how I came up with it. Okay, nice. So dynamic layouts would be saying, oh, let's do a specific layout for that problem we're solving at that particular moment in time.
Yes.
Okay. And how so Feltrade on YouTube is asking when we were talking earlier about wasting space. He says, which space are we talking about when we talk about wasting space? And I think specifically, so Feltrade is a fairly technical user, so you can don't hesitate and give a more specific answer. But from what I understood, is we're wasting trace cells. Is that correct? Is that accurate?
Yes, it is correct. The analogy was silicon space, but in our case it's trace cells. Yes.
Okay, so for each built-in that you want to include in the layout, you use some space cells. So if you add them and you don't use them, then you're wasting trace cells.
Exactly.
Right. So, okay, so dynamic layouts are about changing a layout for every time you want to prove something different. So where does that, like, how do you actually make this work? Does this mean that you need to have a program to create a layout every time? Does this change the verifier? How does this, where do you start implementing this?
Yes, it does change the verifier. Actually, the verifier needs to be adaptive to the layout. Until now, we compiled a new verifier for each layout. That's why it was static. And now we have a verifier that gets the layout as input. On the prover side, what we actually need to do is first run the Cairo code in a simulated environment and measure the execution resources, and only after that compute the optimal layout for it, and then we can create the proof with that specific layout for that specific program.
Does this add a delay in the proof production process?
Not something noticeable.
So all of these steps are things that we had to do anyway, because running the program and then figuring out what the usages of the built-ins and what the usage of the memory is something you have to do even with constant layouts. So the only thing we're adding now is that you have to compute what the optimal layout for the program is, and that's a pretty simple computation. It's just technical.
Yes.
Nice, interesting. And so if you have a dynamic layout, it opens the door to what I was mentioning earlier, meaning you could have more layouts and you could select just the one that apply to your specific proof and use them appropriately. Is that correct?
It's not exactly more layouts.
Sorry, more built-in.
All the more built-ins, and all the parameters are configurable in running time. So we don't have a small set of layouts that are possible. Actually, every set of parameters that you provide will pass, or at least up to some constraints.
To clarify though, the verifier still has to be aware of all the built-ins that you might use in the program beforehand, because the constraints have to be coded into the verifier before you start running the program.
Understood.
That's correct.
Okay, so you don't need to update the verifier as much as you did, because so previously when you added a built-in, you would have to update the verifier, and when you change the weight of each built-in, how much time you can use it for each layout, you would have to update the verifier. Now you don't have to do this second part. You can use a different layout every time. But if you want a new built-in, you have to update the verifier.
Right, that's correct.
Do you think, I mean, you're on the built-ins team. How many built-ins should there be? Do you think there will be a lot, or do you think there's a point after which it won't be very useful to do built-ins?
Well, it depends on the number of use cases. Actually, every use case can have its own built-in. So, so I think that the answer is that it will always grow and grow.
Interesting. Nice. And do you think how feasible it is, do you think, for teams external at StarkWare to write their own built-in?
At the moment, it's the prover is not public, so it is not. The prover is not public, and the verifier is defined by StarkWare. So at the moment, it is not given to the public. But in the future, when they will be the prover and the verifier will be open source and could be changed by the public, then yes, it will be possible.
We have found though that developing built-ins soundly can be a very hard task. So if someone is trying to develop code that might require a built-in, they should consider using simpler built-ins that already exist in the ecosystem before they try to develop one. It's analogous again to trying to develop your own ASIC versus trying to use components that already exist on the market.
Fair enough. Though I would say that, like, for ASICs, you know, it's a spectrum there. Like, for some ASICs, the main cost of ASICs, I guess, is that you then have to, I mean, finding a foundry and actually creating your own ASIC, it requires volume, it requires a lot of capital, but people can still get the skill to design their own ASIC. And to a certain degree, you could design your own IC. So, I mean, like, it feels still like building your own built-ins is a bit, there's less fire of capital to building your own ASIC. I don't know. Does that make sense?
I believe that everything that I can do, someone else can do. So if we can build built-ins, then also other people can do it. Maybe it will take them time to learn the system, as for us it took time to build the system, but eventually it will happen.
All right. So Robert is asking, what happens if someone develops a malicious built-in?
Well, it depends on the way that the proven verifier will be updated in the future. I guess that it will. There will be audit for everything for every update. You don't allow everyone to develop something that you need to trust very securely.
Yeah. And I guess
in general, running a malicious built-in would be like running unsound Cairo code. If you write a program that's not secure, then it's not going to be secure. And the same goes for
yeah, but I guess it also depends on what malicious means, whether it returns something faulty or whether it alts the proving system. But I'm guessing that if there were a built-in that crashes, I'm not sure I'm using the right word, right? But that creates a situation where you can't prove what happened.
I think that malicious means unsound. That a malicious prover can prove wrong statements using this built-in.
So in the Cairo one, in the ecosystem that we are developing, where everything will be complete, also, then you could also have a malicious built-in that doesn't necessarily is not satisfiable. It can't run, and that's also a problem, which is part of the reason I think for the moment we don't allow external built-ins, and it will have to be solved if we're trying to build this in the future.
Nice, thank you. Okay, cool. So technically, I understand that this is it's a very important step for backend, for proving. So What will that enable exactly? Like faster proving, cheaper proving? What's the outcome of dynamic layouts?
Yes, exactly. It will allow uh, it will allow proofs that are dedicated for the statement in a way that there is almost no waste of space, which is very important for the total running time, for latency, for throughput, actually all the efficiency of the system. And of course, it will lower fees, I guess.
Nice. Do you know when this will be live? Do you have a rough estimate of what timeline we're talking about here? Is it something you guys are starting to work on, or is it something that
No, this is in very progress. Like we are close to finishing it. I can't say the exact date, but it will be in 2023.
Oh, nice. That's pretty cool. Super cool. All right. And what will be the impact of this on people writing Cairo 1 code? Like, if I'm writing some code in Cairo 1, do you have to pay attention to this? Will I have to change my code?
No, actually, as I said, different layouts can run the same code. And of course, the dynamic layout also can run the same code, but it will be more suitable. So developing the Cairo 1 code is separate from the machine on which it will be running.
So it will have no impact on my workflow, my code. I will just reap the benefits from lower fees.
Exactly.
That's a nice deal. I like it. Cool. I think, yeah, on my part, that's most of the questions I have. I think this is clear to me now. I'm going to take a look if there's more question. So Tekak is asking, is it theoretically possible to compress the execution trace in some way that provers can still generate valid proofs? One way would be to provably decompress it. So to compress the execution trace in some way that provers can still generate valid proofs. Is this recursion? I don't know.
I'm not sure.
I'm not sure I
I
understand the
understand the
question either.
question.
So Tekak, if you can reformulate your question or elaborate a bit on it, that would be very useful. But to me, recursion sounds like something that would help do what you do. So Robert is saying, how is the verifier determining the number of built-ins used in the contracts? How is that link happening exactly in the verifier? How do you tell him, hey, this is the layout we're going to use?
Depends which verifier you're talking about. I guess you give it you give the verifier as input. This is the layout, and these are the built-ins, and this is what you should verify, and then it verifies it the same way that the static verifiers do, but now it also uh, it has branches and parameters that are runtime instead of being static. That's all the difference.
Okay. I guess the question could be like, how do you represent a layout in the verifier? What is it? It's
Okay, it has several parameters. They are all integers. You have ratios of all the built-ins. You have component step, memory step, things that are very technical. It's just a list of integers, actually.
okay. So you just actually specify the actual number of things you're going to need, right?
Exactly.
But again, this is not something the user should ever worry about. It's something that when we run Cairo code, we input ourselves the prover.
Yes, there is a function that gets execution resources and computes the optimal layout for these resources.
Nice. So Feltroid is asking, how is the cost of a built-in determined in terms of Cairo steps when one is calling it from a Cairo program?
Well, it's the
So I'm guessing, I don't know if he's referring specifically like the number of trace cells, which I guess just emerged from calling the built-in, or if he's mentioning the cost in gas in Cairo 1. And I'm not sure you guys have the answer to that question.
okay. I have the answer for the trace cells question because every built-in actually has a very strict number of trace cells that it is using. The same as a single Cairo step has 51 trace cells that it is using. So bitwise built-in, for example, uses a bit less than 300 trace cells, if I remember correctly. That's the cost for the prover, for example.
So wait, so that's actually a ratio, right? So if you know the built-in consumes a specific amount of cells and you know that a Cairo step is 51 trace cells, then in a way you just have to divide the cost of your
Yes,
built-ins
exactly.
by 51 and you know how much is a trace cell.
Right.
Okay, and then you can convert it to gas. Okay, Felt,
So
let me know
the
if
gas
this answers the
cost,
question.
the gas cost won't be derived exclusively from the trace cells. If the built-in is extremely computationally heavy, we might have to factor that in too. So
Can you
I'm
expand?
not exactly sure.
Can you expand on that a little bit?
Sure. If you try to run a function that's very heavy for the machine itself to compute, like a very computation intense hash function that deals with many field elements for the machine itself, then we might have to factor the cost of that into the gas cost of the built-in, as well as the traces that it takes.
Why?
So I'm not sure exactly how this is computed at the moment, and I'm not sure if we have completely decided on how to compute it. But you can't just take the ratio of trace cells and assume that this is going to be the gas cost itself.
Okay.
I think that what Alon is saying is that we haven't defined yet how gas cost is defined, so we are not sure yet what's the answer to the question.
Okay. I think I understand. One thing that popped to my mind is that probably dynamic layout make gas metering for Cairo 1 easier because in the static layout world, you have like you know that you're going to incur a cost for all the built-ins, and then you have to divide it amongst like if there's 10 slots and only one person is using it, you probably want to charge her more than if there's 10 that are used. Whereas if you can do a specific layout each time you run it, then you can just have the cost which is closer to the actual cost of the built-in, right, rather than the cost of the possibility of needing that built-in somewhere. I'm not sure I make sense.
You are right that this will make the prover. This is a way to calculate the prover cost, but I'm not sure how how the fees are actually taken at the moment. So I don't know the answer to the user side question.
Okay.
The gas cost, I'm pretty sure, is computed only given the number of usages you make. If you use 10 built-ins, then we don't factor in the fact that we have to embed it in something that has more built-ins in it.
I mean,
In part because we don't.
we don't do it, but we don't do it for every time. But when we price the built-in, we do. Like we take into account that like the built-ins, the price is set by us, right? I think by
Definitely,
StarkWare.
yeah.
So
Yeah.
so
But
we
I
so we
think
do take this into account, the fact that there is some possible loss capacity or something. I don't think we
definitely,
price.
in this sense, I think the price of built-ins is going to be a bit harder to compute rather than easier because it depends on the optimal way to put them into the layout. It is going to be cheaper, so that's a good trade-off.
Okay, cool. So it's gonna be more complex, actually, not more simple.
Slightly.
But okay, cool. But it's gonna be cheaper, so who cares? I mean, okay, cool.
Cheaper is better.
Yeah, always.
Yes.
All right. Let's see if there are other questions. I don't see any. Let me check on Twitter. And it looks like we don't have many other questions. We don't have any other questions, so I think we've covered everything. Is there any specific topic that I forgot to mention and you guys want to talk about?
No, I also only mentioned that it was very nice talking with you, and this was it is still ongoing effort of many people that I want to thank. And
Well, thank you for being with us today. And yeah, please, anytime you guys want to come present whatever it is you're working on or give more details, please don't hesitate. It's always good to have this kind of conversation. And likewise for the people listening to us, if you have further questions down the line, if you're catching up this call in a few days and we're not live anymore, send the questions our way. We'll make sure to give you the answers. These are complex topics, so good questions are always fun. So don't hesitate. All right, David, Alan, thank you for joining me today. And we'll see you soon. Thank you for the work you're doing on proving Starknet, and looking forward to seeing this ship then.
thank you very much.
All right. Have a good day. Cheers.
Bye.